Hello, this is page 6 of the class 15 handout. Let me finish this up. This is our first handout where we talk about acids and bases. And in the previous problem up here that we ended off on, we drew the conjugate acids and bases. We looked up the pKa's for an amine and for an alkane, and we drew the equilibrium arrow such that equilibrium favors the weaker acid. In this second problem, we have only one molecule, an amino acid called alanine. So that's interesting. How can one molecule be both the acid and the base? Well, we could take a look at parts of the molecule. For instance, here we have a carboxylic acid, and that has a pKa associated with it. If you look at the pKa table, there's a CO2H, has a pKa of 5. Let's jot that down. Now the thing is, for an acid-base reaction, you need an acid and you need a base. So hopefully somewhere along this molecule there's a basic atom. And you know, a base has at least one lone pair to grab the proton, and here we have nitrogen there. It wouldn't be this oxygen to grab the hydrogen because this is not very basic, and we can discuss that later. Nitrogen is a basic atom, and that lone pair can grab a proton, and so this is basic. But even before we knew that, we have to find an part of the molecule that's acidic. Well, this H2N part is an amine, and that amine is here. It's the RNH2. See, rest of the molecule NH2, and that has a pKa of 36. pKa equal to 36. And so your conclusion right now for this part is that the pKa of 5 is the acid part of the molecule, whereas this is now not the acid part but the base part. The purpose of the pKa's in this case, at the beginning, is to determine who's the acid and who's the base. So if that is the case, you know that the base grabs the proton. We're not going to draw the mechanism. Actually, the mechanism is you would have another alanine molecule nearby, and that nitrogen lone pair will grab the proton of that alanine. Eventually, all the molecules will be deprotonated and protonated. You see how the base got protonated and the carboxyl group got deprotonated. We called this a carboxyl group or carboxylic acid. Why don't I call this the amine? Right, the one with the nitrogen is called an amine. And we have this. Okay, I'm not going to draw the mechanism. Like I said, you would have to draw another alanine to show the proton transfer. But we do have an empty box for the equilibrium. How do we do that? Equilibrium favors the weaker acid. So here I have the acid on the left. What would I consider the acid on the right side of the equation be? Well, here's your base, and your base, becomes the conjugate acid. And here we have the conjugate base. Okay. Do you know what we have to look up? We have to look up the pKa of this functionality. That's an RNH3 plus. Okay, here, RNH3 plus, pKa of 11. Okay, here we have a pKa equals 11. What's confusing to some students is that, why do I have 3 pKa's listed? Well, the first pair was to determine who is the acid. Once I determine that this is not the acid, it's the base, I ignore this, because it makes no sense to have the pKa of a base. Now, when I look at the equilibrium arrow, I now compare the acids on both sides of the equation, and I see that I have a 5 versus 11. Equilibrium favors the weaker acid, and therefore the weaker acid is to the right. Your bigger arrow should go to the right. And please use, we call these half arrows or fishhook arrows. Make them fishhook arrows and make the one going to the right longer. So, what's the point of this? The point of this is that this doesn't really exist in your body. This does. Called the Zwitter ionic form. This form, Zwitter ionic means both it has a positive and a negative charge, and they cancel each other out. So you form this molecule called a Zwitter ion, which has a plus and a minus in the same molecule, and it's this form that is the major form in your body. Okay. You might think that's a little bit unusual because we've been talking about charged molecules being less stable than neutral molecules. Well, that was in the context of resonance, where a charged contributing resonance contributor is the minor contributor versus the neutral contributor. And it's kind of a rare case. That's when we have what's called, remember the separation of charge? And when we're talking about resonance and how to choose the major contributor, one that has a separation of charge is less stable or less contributing than the one that doesn't. Okay, I won't mention anything more about that. Remember to identify the acid on each side, the acid and conjugate acid, and choose the weaker acid for the equilibrium. If an acid is very strong, then it makes sense that it will want to donate a proton. And so we do have the charged species be the major species because this is a relatively strong acid and this is a relatively strong base. I know it's a strong base because it came from a weak acid. Right, remember that phrase? Anyway, equilibrium favors the weaker acid. Try to understand the terminology. Why do I say protonate and why do I say the base is deprotonating the acid? So this functionality becomes deprotonated. This functionality becomes protonated. Another terminology that I want you to be comfortable with is when I say the most basic site. So I'm looking at this molecule and I'm trying to figure out who is the most basic site. Is it the nitrogen? Is it this oxygen? I kind of gloss over why it's not this. It's not this because if I protonate this oxygen and there's an H here, that's actually very acidic. So do you remember the phrase, the stronger the acid, the weaker the base? And so I'm still using that relationship to figure out who are my strong acids and who are my strong bases. In this case, this is a stronger base than oxygen. We could go over that in drop-in hours if you need more clarification or need more examples. Okay, let us pull together everything we've learned about acid-base and pull in some resonance. Okay, so this is a good test whether you understood concepts from different classes. Class 10 was resonance, class 15 was acid-base. Consider this example where there are two basic sites on acetic acid. And so this is acetic acid, and when I say basic sites, which atoms can grab a proton? It could be that oxygen, or it could be this oxygen. And I have the same molecule down here, and I'm going to show you the two different situations. And sulfuric acid is a stronger acid than acetic, so it's kind of weird. This is acetic acid, but it's going to be acting like the base, or it's going to be the base. That's only because the partner is so acidic. Sulfuric acid is very acidic, and this will be the acid. It will donate the proton. What are the two possible acid-base reactions, and which one would occur more often when these two are mixed? Explain without using pKa values. Interesting. If I use this top oxygen as the base, I get something like this. If I use this oxygen as the base, I get something like this. Okay. Go ahead and pause the video and draw me the conjugate acid and the conjugate base on the right side. Let's do the conjugate acid here, conjugate base here, conjugate acid here, conjugate base there. Plus and plus. Okay, hopefully you've done that on your own. Let me show you how I would draw them. The conjugate base would be this. Use purple. So I'm protonating the top oxygen, right? So here we go. And the conjugate base would be the O minus SOH. The conjugate base here is the same thing, right? The O minus OH. But here, the conjugate acid, now I'm protonating this oxygen. Did you have this? If not, make your corrections. Okay, don't forget the charges. Okay. Oops, don't forget the charges. Alright. You mix these two molecules. One of these is better than the other. Right? We're asking you what is most likely to happen. Well, now you have to check the stabilities of your conjugate acids. Because whichever conjugate acid is more stable, that's the reaction that will happen more often. Maybe 90-10. So, for instance, when we mix these two, maybe 80% of the reaction gives me this, and 20% of the reaction gives me that. Okay? Because it's a strong acid, we will definitely protonate the majority of acetic acid. It just depends where. The clue is this. Find the most stable conjugate acid, and that's the one that's going to happen the most. Find which is more stable. We'll call it the product, right? The more stable the product, the more of it you'll make. Okay, I've stalled enough. How do we figure this out? Who can spread out the charge better via resonance? Take a look at this. This is why class 10, weeks ago, is so important. You have to recognize molecules that have resonance, and this one can do this. Look at that. So I have an OH now, no double bond. Now the double bond is here, and this oxygen is positive. I have two resonance structures. Spreading out the charge is stabilizing, right? We delocalized the plus charge via resonance. That's good, right? That is good. Stabilizing. Stabilizing. Some of you probably are asking, can we double check this? Yeah. Let's see if this has any resonance. You know, this has a lone pair here. You know, think about it. If I move the lone pair here, man, what's that oxygen going to be? That oxygen's going to have a double bond right here. Former charge equals 6 minus, if I make this like that, okay, there would be double bond here and no lone pair. That's 4 sticks and no lone pairs. No balls. See, that is a +2. Yikes. That is bad. We've never seen an oxygen that's +2 in organic chemistry, in an organic molecule. Yeah, obviously, when we make the double bond, we would have to do that also. But I'm concerned about that oxygen. If that's +2, that is invalid. This movement of electrons is invalid. I tried to make another resonance structure and I failed. You know why? There is no other resonance structure for this. Now, some would argue I could draw that only, but you see, that would create separation of charge. That would be a minus, a plus, and we did nothing to this plus charge. What I'm saying is, there's no way to move these electrons reasonably to spread out this charge. Whereas up here, there is a reasonable movement of electrons to spread out the plus charge, and now it's shared between these two oxygens. This is more prevalent, and what's our final conclusion? This oxygen is more basic than this oxygen. So I would say, using our terminology, this is the most basic site. That would be my final conclusion, and that's how I would answer this problem without using pKa's. Now, how would I use pKa's? Well, I would ask, which one is more stable, which one is less acidic, right? The less acidic conjugate acid is the more stable one. The more stable one is the one that's made preferentially. Okay. Alright, so that is a challenging problem that I expect people to be able to do once they understand better these relationships that we've seen with acid-base reactions. In class 16, our final class of new material before the exam, we will now learn how to predict acidity without the pKa values. And as you can guess, we will be using some resonance to figure out the stability of our conjugate acids. Give me 1 second. That's the base. That's the base. That's the conjugate. Okay, good. Yeah, stability of the conjugate acids. All right. I will see you on Monday.